All right, folks, it's Bass Action back in action here. In this video, we are primarily going to focus on systems of nonlinear equations. However, our first example is a system of linear equations. These are both lines. I've included this particular example because I want to both emphasize and discuss the final answer of this, but I also want to talk about how we are going to handle these fractions. It is really, really important that you get in the habit of clearing your fractions before you start doing any work. Not clearing the fractions is where I see most students make their mistakes. So on this problem, the first equation, I'm going to multiply everything through by 2. And on the second equation, I'm going to multiply everything through by 4. That's going to give me a 5x minus a 2y equals a negative 8. And then on the second equation, a 20x minus an 8y equals a 1. Now from here, to solve this system of linear equations, I want you to get in the habit on these to work with elimination. So that means we need to eliminate either the x variable or the y variable. I'm going to choose to eliminate the x's, and I'm going to take the first equation and multiply everything through by a negative 4. That leaves me a negative 20x plus an 8y equals a positive 32, and the second equation stays the same, 20x minus 8y equals a 1. I can now add these two equations together, and when I do that, all of my variables drop out. So the left-hand side becomes 0, and the right-hand side is 33. Now, obviously, 0 does not equal 33, so this statement is not true. If you end up with a statement that is never true, all the variables are gone, the statement's never true, your answer will be no solution. Meaning these two lines do not have any points in common. If you end up with a statement that is always true, 3 and 3, 0 and 0, 7 and 7, if it is always true, the answer is infinite solutions. If we were to go and graph these, all right, so, and we'll do more of this in class, the graphing aspect, but if you were to type these two equations in Desmos exactly as they are originally written, what you will find is that you have two parallel lines. And since the parallel lines don't have any points in common, they'll never intersect, that then syncs up with our answer of no solution. Now let's take a look at our systems of nonlinear equations. In these cases, I'm giving you an equation for a line and an equation for something else, in this case, a line and a quadratic. On these problems, more often than not, you'll be using substitution. What I would suggest on this one is I would take your equation for your line and I would solve it for y. So x plus 3 equals y, and now here's our y and here's our y, so we can use our substitution. So x plus 3 equals x squared minus 4x plus 7. We've got a quadratic, so we're going to move everything over to the right-hand side to keep our quadratic term positive. So we'll have 0, x squared minus 5x plus 4. We want to get in the habit of factoring. We do not need to use the quadratic formula here. We're thinking multiplying to a positive 4, but adding to a negative 5. So our x values are 4 and 1. Now, the important thing to understand is that we're solving this system, we're looking for points of intersection. So these values for x are only the x coordinates of the points of intersection. We do need to finish the ordered pairs, and I would strongly encourage you to use the equation for the line for that. So this y coordinate here is going to be 4 plus 3, or 7, and this y coordinate here will be 1 plus 3, or 4. So our final answer will be these 2 points of intersection. Then I've got one more system of nonlinear equations for us to look at here. Again, I gave you the equation for a line, and then I gave you an equation for something else. This other equation, if you don't recognize it yet, which you haven't had a lot of experience with it, this is actually going to be a semicircle. okay? This, if you go back to our circle unit where we wrote the equation for the circle as the two separate pieces, the top and the bottom, that is what this equation is here. Now, what I want you to notice, these are both already equal to y. So we can just right away set these equal to each other. X plus 2 equals the square root of 4 minus x squared. To solve this, we're going to square both sides, but there is a common mistake that happens on this particular problem. When we square this binomial, and it's a really, really easy mistake to make if we're going too fast, we need to remember to multiply that x plus 2 by itself. So x plus 2 times x plus 2. The right-hand side is just going to cancel out that. This exponent is going to cancel the radical, so 4 minus x squared. Let's expand the left-hand side. X squared plus 4x plus 4 equals 4 minus x squared. Let's get everything over to the same side since I can see I've got some quadratics, so I'm going to move that over to the left-hand side. I've got a 2x squared plus a 4x. When I subtract my 4, it cancels out, and I'm left with 0. This leaves us with a quadratic that doesn't have a c value. So what we want to remember here is to factor the GCF on these. Otherwise, we have a tendency to lose a solution. So in this case, we're factoring out a 2x, and we're going to be left with x plus 2 equals 0. So my x values are 0 and negative 2. But just like the last problem, these values are only the x coordinates of these ordered pairs. So I would get in the habit of writing them like that, and then we're going to come back. We're going to use the equation for the line to finish off these ordered pairs. If x is 0, the y coordinate is 0 plus 2, which is a 2. And here, we're going to have a negative 2 plus 2, which is going to be 0. Those can get really kind of confusing and students mix those up. So I would strongly encourage you to get in the habit of once you get these x values to write the ordered pairs and then substitute in from there.